Okay, so essentially, like Janita said, catalysts are about speeding up chemical reactions. So let's talk about what chemical reactions are, right? So essentially, chemistry is happening everywhere around you at all times, honestly, right? Inside your body right now, you are undergoing a chemical reaction to convert the glucose that you have into usable energy. You're using the air that you breathe for that as well. And at the same time, plants outside, they're converting sunlight into glucose as well. The computer inside is converting chemical energy into electrical energy. Chemical reactions are happening all around us at every moment. Another example, acid rain reacting with concrete, frying an egg on a stove, metal rusting around us. These are all different types of chemical reactions. Okay. So inside our body itself, it's approximated that we have about 37 billion chemical reactions that happen every second, because there are trillions upon trillions of cells. Each of those cells are doing some kind of chemical reaction. So there is a lot of chemical activities happening in your body, okay? But we refer to them as biochemical reactions because biology and chemistry interrelated, and that's happening inside your body. So we call it biochemical reactions. So essentially, any reaction requires energy to be done, okay? For something to react, it needs energy to start that chemical reaction, okay? So biochemical reactions actually require a lot more energy than we end up using anyway to begin with, right? They actually need a lot of energy to be carried out, but life actually found a shortcut, okay? Life ended up using an enzyme, which is considered as a catalyst, a biological catalyst, to lower the activation energy required to do a chemical reaction. Okay, so if the energy required to do the chemical reaction is up here, a catalyst lowers it to this point where it can undergo the chemical reaction. So essentially, the chemical reaction can happen faster and at a quicker rate, meaning more can react at a quicker time, and also more of them will react as well. So this is how enzymes catalyze a reaction. They act as a catalyst, and catalysts basically speed up reactions. Okay, so connect the idea you have a catalyst with enzymes, because enzymes, they are referred to as biological catalysts. Okay, they speed up the reaction, so that's why we consider them a biological catalyst. So certain things to note about enzymes, okay? So they work by having a substrate bind to them, okay? So if the enzyme, excuse my drawing, it's going to look horrible. Yeah, if that is the enzyme, it has something known as an active site, okay? On an enzyme, that active site is where the substrate will bind to. Okay, so through the binding of the substrate to the enzyme's active site, it will undergo the reaction of catalyzing it. Okay, what it does, we're going to look at in a bit, but just remember that enzymes have an active site, and that active site is where the substrate binds to. Yeah, oh shit, sorry. That did nothing. There you go. All right. So another thing to note, enzyme is specific. Each enzyme is specific to each substrate. Okay. So for example, when you eat your food, you're chewing it in your mouth, an enzyme is used to break down some of that carbohydrates. It's called salivary amylase. Okay. That salivary amylase can only bind to the specific substrate it binds to, which are carbohydrates. Okay. It won't bind to any proteins. It won't bind to any lipids. It won't even bind to anything that is not the specific carbohydrate it was programmed for. Okay. Even if it's slightly different, it won't bind because they're very shape specific. Okay, enzymes are very shape specific. So the reason I give these two gaps here is because each enzyme will be shaped differently, having a active site that is also shaped differently. Okay, the reason why they're shaped differently is because they're targeting for one specific substrate, and they want to make sure no other substrate binds to it. Okay, only the one targeted substrate can bind to it because it has the specific lock and key model. Okay, one lock will fit into one key, and they will work for each other. It's the same thing with enzyme. Okay, enzyme is a lock, the substrate is the key. They can only come together when they find the right copies of each other. Okay. Next thing, they are reusable. Okay, a lot of the things in our body tend to be reusable, such as enzymes. Okay, so enzymes, even after they've broken down the complex molecule into a simple molecule, it can still do it again and again and again. Okay. Next thing is that, like I said in the past, enzymes will always end with the ASE at the end, the suffix ASE. So it's an easy way to identify them, right? Lactase, amylase, maltase, galactase, sorry, RNA polymerase. All of them will have the A's at the end. That's why they are referred to as enzymes, okay? And another thing to note, not all enzymes are proteins. Certain RNA molecules actually behave like protein as enzymes, such as ribozymes. This is a footnote that you need to remember, but 95%, 95 to 99% of all enzymes are proteins. So it's just a technicality in case they ever ask you that whether any exists at all. Right? So another feature, like I said, enzymes have active sites. This is where that substrate will bind to, okay? So let me zoom in and let's show you guys. All right, basically, this is the lock and key model that I was talking about, right? The fact that this is the substrate, this is one molecule, okay? Lactose molecule, okay? It will look for lactase, the corresponding enzyme. You can always match them because their names will look very similar, right? Lactose is the substrate, lactase is the enzyme because ASE at the back. So that is the enzyme. This molecule can only fit to this enzyme. They are very shape specific to their binding site. So the enzyme has active sites where the substrate will bind to, and the substrate will have a binding site which it will use to bind to the active site, right? So once it binds, the shape will conform to each other. Okay, the binding will allow them to undergo conformational change to actually stick together better, and the enzyme then is able to actually break down the molecule, is able to support the chemical reaction of breaking down the molecule into simpler molecules. Okay, so lactose is what it started as, and then through the chemical reaction, it was separated into glucose and galactose, right? So enzymes allow for this to happen by lowering the chemical energy, lowering the activation energy needed for this reaction to occur. Okay, essentially the reaction is just breaking up lactose into glucose and galactose. Okay, only thing that the enzyme is doing is by binding to them, it has lowered the energy required for that reaction to occur. Okay, it is not doing the reaction. This is a very important thing to note. The enzyme is not carrying out the reaction. It is simply lowering the activation energy required to carry out the reaction. Next is it's reversible. So like I said, it's breaking it down, but the same enzyme can be used to build it up as well. I'll show you guys that in the next slide. Next is that they're organic catalysts or biological catalysts. Okay, because their function is similar to catalysts, which are about speeding up reactions. This also speeds up reactions, so we call it a organic catalyst or a biological catalyst. So remember how I said that most enzyme catalyzed reactions are reversible, meaning that it can be used to build up molecules and also break them down. The same enzyme as well. Okay, so we have the substrate, which is a molecule, the complex molecule, the enzyme, which is supporting lowering the activation energy to break it down, and the product, which is what we get when we break it down. Okay, so product can be made into substrate using the same enzyme, and substrate can be made into product using the same enzyme. So that's what it means to be reversible. It can go one way or the other. That will depend on a bunch of factors. Okay. That is not a good sign. So this is referred to as anabolic or catabolic. Okay. When you are using small molecules, assembling them into a bigger molecule, it's anabolic. When it is breaking it down, a complex molecule is being broken down into simpler molecules, it is catabolic. Okay. Essentially, the easiest way to think about that, when you eat meat, you're eating a protein, right? You're essentially just eating the protein. That needs to be broken down into an amino acid for your body to absorb it. Okay, so that is a catabolic reaction. Breaking down proteins, which are the complex molecule, into its simplest form, which is an amino acid, that is catabolic. Yeah. So they would say that this food has an amino acid, but the thing is, when it exists as it is, it's already built up into a protein. Your body then breaks it down into the amino acid. So bread, that's carbs, right? There's full-on carbs, but carbs is essentially glucose. It needs to be broken down into glucose, right? That is a catabolic reaction. Your DNA being made, that is an anabolic reaction because you're building up a complex molecule from simple monomers. So that is anabolic. From DNA, transcription, that's anabolic. What else? Hybridization, condensation reactions, they're going to be anabolic because they're building something from smaller molecules. Right? Muscle growth would be anabolic because it's building up rather than breaking it down. If you are breaking down your muscles to get energy, that is catabolic. Your muscles, the proteins are basically being eaten up to make energy. All right. So how do enzymes work? It's very much associated with their structure, okay, the way that they are designed. Okay, that has to do a lot with their function. First thing is that, remember, each enzyme has a specific shape based on their substrate. It's not always going to be the same structure. It can be different. Sometimes it can be very different even, but they are designed that way because they have something that needs to be able to bind to them, right? In this example, this substrate can only ever bind to this enzyme. This substrate cannot bind to that enzyme or that enzyme because its shape is only complementary to the other enzyme. Okay, so when a substrate binds to the active site, it forms something known as the enzyme substrate complex. Okay, which is basically a structure made up of the substrate and enzyme being connected to each other. So here you go, you see one enzyme substrate complex. Another one is this one, where the substrate has bound to the active site of the enzyme. They form one structure together. That structure is referred to as the enzyme substrate complex. You guys need to know why it's called that. And then once they've bound, the chemical reaction can take place, breaking it down into the products that we want. So the three phrases that you guys need to know, go through, is that it starts out as a substrate, then becomes part of the enzyme as a enzyme substrate complex. And then once the chemical reaction happens, it becomes products to be released, right? So the products will depend on the enzyme and the substrate itself, but basically this is what it will look like. Yeah. So when the substrate binds to the enzyme, a few things happen. Okay. First thing is that the enzyme undergoes conformational change to allow it to bind better with the substrate. So basically, it's like someone hugging you tighter when you hug them. Like they just want to secure you more, right? The same thing with enzymes. When the substrate binds to the enzyme, it will change its shape slightly to better hold the substrate in place. Once it does that, it will experience multiple bonds linking them together. Okay, you don't have to know the name of the bonds for this one. Just know that multiple bonds are formed between the enzyme and the substrate to allow them to stick together no matter what. Okay, this is until the chemical reaction can take place. So this is what we refer to as the induced fit model. The fact that if after the substrate binds the enzyme actually changes its shape slightly to better bind it, right? So substrate binds to the active site, enzyme changes its shape slightly as the substrate binds, allowing the enzyme substrate complex to form. Substrate is then converted into the products, and then that product is released. Oh. So what does that mean exactly? But like, does that mean you don't need to do lockout? Oh, okay. I'm not sure how that works, but okay. All right. Once the substrate is in position, the reaction can take place, right? So essentially, you don't need to know much about the reaction because that is chemistry already. Okay. The only thing you need to know is that they include the enzyme above the arrow when we have the chemical reaction occurring, right? So this is our reactants, that's our product. This is our arrow to signify a chemical reaction has taken place. Above the arrow, they place the enzyme to indicate what catalyzed the reaction. Okay, so we have hydrogen peroxide. Catalase is the enzyme. Sorry, catalase is the catalyst that breaks it down into water and oxygen. So catalase will be placed above the arrow. And another example down here, right? So we have lactose, that's our substrate. We have glucose and galactose, that's our product. In between is the chemical reaction, and above the arrow, that's the enzyme that was used to break it down, to facilitate breaking down the substrate. Okay, any questions about this? Essentially, all you need to know is that enzymes lower the activation energy required for a chemical reaction to take place. That's talking about almost all the chemical reactions in your body will require an enzyme to lower the activation energy so it can do it at a quicker rate. And when we do that, when we write it in a form of chemical equation, we place it on top of the arrow to signify that it has sped up the reaction. What? Multiple times? Annoying. Okay, so now let's talk about what is activation energy, right? We've been mentioning multiple times that enzymes lower the activation energy of a chemical reaction to take place. But what is chemical activation energy essentially? Okay, so for a reaction to take place, atoms have to collide with each other. Simply put, right? Atoms have to collide with each other for a reaction to take place. Any chemical reaction to take place. Even something like rusting can only take place when the particles collide with each other, right? Water particles collide with the iron particles. That will facilitate the chemical reaction. In our body, it's the same thing as well. There needs to be particles colliding for a chemical reaction to take place. But not just because they collide doesn't mean that they have undergone a chemical reaction. They need a certain amount of energy when they're colliding with each other for the reaction to occur. So you can see here, particles collide without enough energy to react, they'll just bounce off each other like any other day, right? But if they had the right amount of energy when they collided with each other, they can actually undergo a chemical reaction to bond them together even. All right. So as long as that energy is provided, a chemical reaction can occur. So under collision theory, chemical reactions can only occur when the atoms collide with each other with the right amount of energy. Okay. So I know it's still a bit confusing, so I'm going to get you guys to watch this video. Hopefully it clears things up a bit. Hmm? I'm gonna play the video again because all right, beyond this, you don't need to watch really. All right. So essentially, that activation energy is the initial hurdle for a chemical reaction to take place. Okay. Every chemical reaction has a hurdle to take cross over for that reaction to occur. Enzyme basically lowers the hurdle. There you can go. All right. That's basically all that enzyme does. It lowers the activation energy required. So you can see here, let's compare these two together, right? All right. So this is a biochemical reaction that occurs without enzymes. This is the same biochemical reaction with an enzyme. Okay. On the left, you can see that it required a lot more energy, a lot more collisions, a lot more kinetic energy for the atoms to collide with each other in the right way for the reaction to occur. Whereas with an enzyme, the atoms didn't need as much energy to collide with each other in the right way. So the activation energy required for the chemical reaction to occur was much lower. So enzymes basically facilitate the collisions to occur such that the chemical reaction can happen without a lot of energy need. All right. Uh, So this is the case whether it's anabolic or catabolic, whether it's building up a molecule or whether it's breaking it down, enzymes will lower the activation energy required for either one. Okay. To build things up, it requires a lot more energy than to break things down. Okay. So essentially, a process like DNA transcription is very energy intense. A process like protein synthesis is very energy intense. Whereas a process like digesting proteins in your body when you eat them is very easy. You do it much more uh, it requires much less energy in your body because you're breaking something down versus building something up. So the phrase building something is always harder than breaking it down. It's very much the fact here. Okay. So because enzymes lower the activation energy, they inadvertently make the reaction time much quicker. Okay. So remember, enzymes just lower the activation energy. As a result, the reaction time is faster. Okay. They don't increase the reaction time, they lower the activation energy. As a result, it increases the rate of reaction. But one thing to very importantly note, reactions can still occur without enzymes. Okay. They are not going to be stopped by not having enzymes. all that's going to happen if there are no enzymes, that it's going to take a longer time for the chemical reaction to occur, right? Because it needs more time for it to get the necessary energy, and then only it can react. Whereas with enzymes, that is a much shorter goal. Okay, essentially, think of it as a goal that it needs to reach to undergo the chemical reaction. With an enzyme, without an enzyme, the goal is 100 plus. Okay, with an enzyme, the goal is more like 15 plus only. So it's a much shorter distance to travel, so it will get across much quicker. Whereas without an enzyme, it's a much longer distance to travel, so it'll take a longer time for it to be able to do it. That is an analogy for you to try to think about it. So it's very important that you guys remember this, the reaction can still take place. Okay, so any breakdown of carbohydrates can still take place without the enzymes in your body. It just takes a lot more energy for it to occur. So step by step, let's go through it again. Enzyme has an active site. This is where the substrate will bind to. This is the substrate, which is a complex molecule that has a bond between, so it has a bond that's keeping them together, making it a complex molecule. So when the substrate approaches the enzyme, it sees whether the shape is conforming with each other. Okay, think about this. Enzymes and substrate are floating around, right? They're colliding with each other. Every time they do, they check whether they're complementary to each other. Only if they're complementary, they will form the complex, which is the enzyme substrate complex. Okay, once it's formed that complex, it will, sorry, once the substrate binds to the enzyme will change its shape slightly to conform better with the enzyme, to hold it better, basically. That's when it forms the enzyme substrate complex. So through the binding, the activation energy of breaking the bond between them has been lowered a lot. So it happens faster and it's broken down already. So there's no more bond between them. It allows the products to be released, which are glucose and fructose, at which point the enzyme then looks for another substrate to do the same thing. Okay, enzymes are reusable. They are very specific to their shape. They have active sites that allow for the binding of substrates. And what else? They're made up of proteins 95% of the time. Okay, those are the important features to note about the enzymes. So just now the video was talking about collision theory and how you can do a certain things to increase the collisions, right? For example, increase temperature and so on. They can actually work with enzymes as well. There are certain things you can do to make an enzyme work better. We will look at that in the next lesson. But this lesson, make sure you guys understand what an enzyme is and how an enzyme works. Okay, an enzyme is a biological catalyst. And what do? They catalyze chemical reactions. Enzymes specifically, they catalyze biochemical reactions. Okay, catalyze means that it lowers the activation energy required to carry out the chemical reaction. It's important that you make a distinction between carrying out the reaction and lowering the activation energy. Enzymes do not carry out the reaction, they simply lower the activation energy, allowing the reaction to occur. The chemical reaction would be able to occur whether enzymes are present or not. Enzymes simply make it faster by lowering the activation energy. So enzymes, there are approximately 75,000 enzymes in your body that are constantly working. And they usually are going to work in one biochemical pathway. Okay, a biochemical pathway is basically where enzymes are constantly teaming up to break down a complex molecule into its simplest form, or something along those lines, right? So biochemical pathways are a series of enzyme catalyzed biochemical reactions in which the product of one reaction becomes the substrate of the next reaction. So this is when an enzyme breaks down a substrate into products. The products that are formed are then broken down into another product using another enzyme. So we start here, right? Oh no, the one above here was taken away. So imagine there's something here, a substrate. This enzyme broke that substrate into this product, but this isn't the end goal. We want this to be the end goal. So this is then broken down into this product by this enzyme, and so on and so on. When there is a pathway formed, we refer to it as a biochemical pathway or a metabolic pathway. It's basically a line that shows a complex molecule being broken down step by different enzymes until we get to the most simplest version of that molecule. So the best way to think about it, think about the food that you eat. The food that you eat is at its complex stage, right? Carbohydrates, fats, and proteins. These are the complex versions of the nutrients that you need. Those nutrients are then broken down in your digestive system using these enzymes. Okay, a very straightforward biochemical pathway you can remember is the one for your carbohydrates. Okay, when carbohydrates enter your mouth, they're broken down by a enzyme called salivary amylase into maltose. Okay, when you swallow, it goes into your stomach, goes into your small intestine, where it meets a bunch of other enzymes that further break it down. Okay, maltose into sucrose, sucrose into galactose and glucose. If I'm remembering correctly, there are a lot of them, and they all vary slightly. Yeah, so it starts with glucose, salivary amylase breaks it down into sucrose. Sucrose is then broken down into glucose and fructose. Okay, this is the biochemical pathway. Each step is using a different enzyme, but they're all trying to work together to get the final goal, which is glucose. Okay, that is why it's a biochemical pathway, because it's following one pathway until it gets to the very end. And that's the same for proteins as well, right? When we eat proteins, pepsin and hydrochloric acid in your stomach breaks it down into partially hydrolyzed protein, and then trypsin breaks it down further into small peptides and amino acids, and then it's then transported into your blood. But this is the biochemical pathway because we started out with proteins, and through the action of different enzymes, it was broken down into different products until we got an amino acid, which is the simplest form of a protein, the monomer of a protein. Okay, that's what enzymes do. That's what enzymes are used for generally in your body to break down complex molecules into simpler molecules. But also remember, it can work the both other way as well. Enzymes can be used to anabolize molecules. Sorry, enzymes can be used to catalyze anabolic anabolic reactions. Basically reactions where it's building something. Enzymes can also support that while also supporting catabolic reactions. All right. Yeah, this is basically the summary of everything I talked about. You guys need to remember what it is that we're talking about for each of these. So if I ask you, what about an enzyme is reusable? You need to be able to state it. What about it is specific? You need to know that. What about it is reversible? You need to know that. Why are enzymes about speeding up and not creating? Because enzymes are only there to catalyze a reaction. They do not create any new reaction. Okay, they are basically there as a support. They're not the main character. Okay, they're not going to change the story. They're there to help make it faster. Have an active site. What does that mean? Above the arrow. Basically, this is when enzymes are placed above the arrow of a chemical reaction to indicate it was present. The A's, what does that mean? Act on entire biochemical pathways. So talking about how multiple enzymes can work together, frequently influencing entire biochemical pathways, catalyzing each step. Okay, and then are a subset of catalysts. So if catalysts are a big group of molecules that can speed up chemical reactions, enzymes will fall into that category because enzymes are referred to as biological catalysts. So another way to think about it, all enzymes are catalysts, but not all catalysts are enzymes. Okay. So another example of catalysts are some metal ions. Okay. Metal ions can speed up chemical reactions that occur in nature. So they are referred to as catalysts. Enzymes are specific for life, specifically life in their bodies. Enzymes work to speed up chemical reactions. So they have a similar function to catalysts. So that's why we call them biological catalysts. Lastly, they are proteins. So essentially, you can say that 95% of all enzymes are proteins. But if in case they ask whether there are any enzymes that are not proteins, you need to be able to state that there are one or two enzymes that are made using RNA. Okay, so they behave like a enzyme, even though they're made of RNA. So that's that. Right, some memes, enzyme specificity. Enzymes like to be specific. So yeah. I feel like I shouldn't even explain. I ruined it by explaining. But I feel like I've decent meme game this time.
Thank you.
One enzyme does not simply carry out reactions with multiple types of substrate. It's very specific, is what that means.
So does like determine how fast or metabolism?
Sorry?
No enzymes determine how fast it is.
Do enzymes determine how fast your metabolism is? I would say it's one of the factors, but it's not the end all determinant because metabolism has to do with your hormone levels as well, your thyroid levels and other stuff. So that actually regulates your metabolism much more than your enzymes. So people with a very high metabolism, people who are constantly skinny, even though they eat a lot, they might have something known as hyperthyroidism, which is the overstimulation of their thyroid to make more hormones.
So, my mom actually has that hypertension, and I can't gain weight, so I might have it.
So she can't gain weight no matter how much she eats. Yeah.
No, actually no.
Hyperthyroidism. Yeah, it's a very, not to say very common, but like you do see it pop up. People with hyperthyroidism, when we're learning about hormones, you can definitely relate those two together. It'll actually come up in the topic itself. But hyperthyroidism is when your thyroid is overexpressed, making, forgot what's the name of the hormone, but that directly impacts your metabolism. Okay, if you're under expressing it, it's called hypothyroidism, where you actually gain weight excessively, even though you eat very little. Okay, that is hypothyroidism. All right, so that's it for today, guys. Let me know if any part of today's lesson was confusing. All right. All right. Basically, this is everything we learned today. Any part of this is confusing for you guys. Okay. Whichever part is confusing, please let me know now so I can explain it further. Annie, you came in halfway through.
That's okay, I'll rest your feet.
Yeah. All right. Look at these. I want each of you to read through each one. 1, 2, 3, all the way to 10. Tell me if you don't understand even a single one of them. We can actually look through it. We have about 12 minutes anyway. We have 10 minutes anyway. Thank you for keeping me honest. How was my meme game? Feel like I update this time. Okay, never mind. Enough credit.
It's really hard. Is it the memes or is it because the topic is so hard that no meme can make it funny?
But those memes are so good. Like, seriously.
When you search them up, did you actually like laugh at random?
Obviously, yes. I'm a biologist. This stuff is like the most funniest thing ever. Genetic. I studied Bachelor of Science majoring in genetics. So what we just learned about genes, all that, and also more to come. I have a bachelor's in it.
Oh,
My master's in teaching.
You planning? Oh, did you already do it?
Yeah, I already did my master's. I did my master's. Literally graduated 2022. Who knows? I might do a PhD.
Oh,
We'll see then. That's very much a future plan. What? Offered the school confused.
It like focuses on research.
Oh, interesting. I mean, I'm not sure whether we're going G-Tech at all this year.
No, please no.
Why?
I'm so tired of that place.
Okay, maybe not. Okay. Okay, for the excursion, essentially everything you need to know. I'll put up a video and something to read through by today. So just watch the video, read through whatever I send, and you guys should have the basics of what we need for our EcoLink excursion. But essentially, you guys are going to be dealing with the content that you haven't covered yet. Okay, it's going to be about genetic modification. So it's kind of ahead of what we are doing now. This excursion is going to be a chance for you to try to get hands-on experience doing it. So I'll make sure to let them know that you guys haven't explicitly learned it. That should make them more aware of that. All right. Any other questions? Okay, remember, guys, please submit your consent before the excursion, and please come for the excursion also there. Really didn't notice. Sorry about that. Okay, I'm gonna.
Someone going there. Is it gonna take up the whole day?
Yes. Not a fan? Unfortunately, yes. All right, Mac. No other subject is more important than biology.
Not even English. Math?
You can speak English, right? Like no one's questioning that.
So you don't need English.
Who said?
English is so unnecessary.
Honestly, it is. You can speak it. You're good enough.
Well,
Like, I don't care about becoming a scholar in English. I guess we have a very similar way of thinking. All right, Mark. Whichever one, does any of them make sense? First question. That's not a good sign. Let's go through each one of them. Okay. First, enzymes are reusable. Do you get that? Okay. Second, enzymes are specific. They're almost like puzzle pieces. One will only fit to the other. Next, they can be reversed as well. So whatever they break down, they themselves can build it back up. So the enzymes can catalyze breaking down a reaction or also building up reaction. All right, next, they're only speeding up reactions. They're not creating a reaction by themselves, okay? So even if they're not there, the reaction can still take place. It's just going to take much longer. Next, enzymes come with active sites. That active site is where the substrate binds to, okay? See the board? Enzyme, active site. The active site is where it will connect to. And those active sites are where the specificity is implemented. The way the active site looks like is going to match with the right substrate. They're made of proteins. 95% of them are all proteins. Some of them are made of RNA molecules, but on average, yeah, it's going to be proteins. So enzymes fall under the category of catalysts. Okay, catalysts are anything that can speed up a chemical reaction. That's why enzymes fall under it, because enzymes essentially just do that. They speed up a reaction. So they are referred to as biological catalysts. There are a lot of catalysts out there for chemical reactions. For example, for rusting, if I remember correctly, a specific metal ion will make it rust faster. So in this one, having the enzyme allows it to happen faster in our bodies. So imagine something as complex as carbohydrates needs to be broken down into glucose. It will have multiple steps, which we call a biochemical pathway. Enzymes can act on every step of that biochemical pathway. Okay, there can be multiple enzymes that break down a substrate into a product, and then that product is used as a substrate for another enzyme. So it's almost like taking multiple steps to get to floor one. Every step is a different enzyme. And enzymes end in ase, the thing you can always use to identify. And that in chemical reactions, the enzyme will be placed above the arrow. Okay, let me show you what that looks like. Yeah, like this, right? See above the arrow, that's where we put the enzymes.